All right, well, good evening, everybody. Glad to see you all here tonight. Big crowd tonight, so this is kind of fun. We got a lot of people in the room, and we have a lot of, we have 2 member presentations and a regular presentation tonight, so we have a lot going on, so it should be fun. Let's get to it here. All right, so as always, for those in the room and those on Zoom, and I think we have as many as 35 tonight on Zoom. We have a big group out there. Thanks for being with us tonight, as always, and I say this every single month. We hope you enjoy yourselves tonight. We hope you learned something new through one of the presentations or all of the presentations tonight. We hope that you make a new friend. We're all here to get acquainted with new people and expand sort of our social group. And we hope you reconnect with old friends as well. Quick cell phone reminder. Actually, I think I have to do the same. Let me check. I've been so busy that Okay, I actually did have to do the same. So anyway, I'm glad I put a reminder myself. Anyway, so everybody got their phones on stun. That's great. Any visitors tonight before we get in? So we like to meet new visitors. Anybody here? You can raise a hand, and Woody, you can get the microphone back there. As you can see, we actually made it really simple for anybody who's new. We're telling what we'd like you to tell us, your name and so forth. So we had a name right there, Woody. Yeah. Okay.
I'm Isadora. I've been to a meeting before. I'm a visitor because I'm not a member. And I just really liked the environment, and the lectures are really great. Everyone's really knowledgeable. It was very interesting. I just like looking at the sky. That's my astronomy experience. I don't have a telescope. I just think it's interesting. My favorite thing about space, I guess, black holes.
Okay. Anybody else here new tonight? We got another one.
Good evening. I'm Les Taylor, and I've always been fascinated with scientific things. I finally found Smith Castor Green, if I said that correctly. And I'd like to look at, is it Messier, if I say it right? I've been saying it many years. I guess it's kind of French as far as astronomy words go, or maybe Latin. But I enjoy doing it occasionally. I've been quite busy in my life, so always enjoy times when I can go out. My last experience was at Oak Creek, south of Sedona. I went up to Flagstaff, and I thought I'd explore that area at Lowell. And of course, the monsoons were up there, and they just kind of set in that area. So they said, you have to go south. So I went to Oak Creek, and I had a lucky night. The sky was clear. I set my clock for 2:30, and I think I saw 5 planets that night. I saw some Messier objects, and it was just a beautiful night, clear sky, and learned some things about where things are in the sky again. Thank you.
Well, thank you. And what a wonderful evening, actually. I wish I'd have been there with you. So anyway, anybody else here new? We have one more behind. Woody, off. Yeah.
Hello, everyone. My name is Tony. I'm new here. I heard about this event, and I go up to Flagstaff pretty often, so I tend to hang out at the Lowell Observatory a lot. Learning about Pluto and all the equipment that's used to discover Pluto was pretty fascinating. Love exoplanets, black holes, everything out in space, so that's why I'm here.
Okay, well, welcome. We're glad to have you. Anybody else here? Yeah.
Hi, I'm Kevin O'Donnell. I found this on, I guess Jim Sellers told me about this originally. I don't know if some of the group knows him, but I've become friends with him and some others online. Reason brought me here because I haven't been to one of these meetings, but Joy has been telling me 100 times to come, so I definitely wanted to come and see, and wow, a lot of people here. That's great for space. Other than that, my astronomy experience is mostly photography. I mean, I took, astronomy in college, but just got into it more recently now that there's digital technology. So that's what I like about space.
Well, welcome as well. Anyone else? I think we've gotten everybody, but don't want to miss anybody. All right. Well, welcome to the visitors tonight. Thank you very much for joining us. Oops. There we go. Okay, tonight's agenda, as you can see, we've got quite a bit going on, and we've got some general announcements coming up here in just a moment. Then we've got several special announcements regarding star parties, clubs, elections, Christmas dinner, raffle, all that sort of stuff. We got two member presentations tonight, one from Bob Buchheim and another one from Ted Berenyi. So we'll have some fun with that. We'll have our short, 15-minute seventh inning stretch. And then we'll have our main speaker, Dr. Alan Strauss, here tonight talking with us. So should be a fun evening. General announcements. These are the same 5 minutes of announcements I do every month. So, and then like I said, we have several special announcements as well. So once again, if you want to join the club or renew a membership or whatever, we do have some new folks here. You can do so if you go out online and look at our webpage. And I've kind of annotated the slide there a little bit so you can see the address of our webpage, but you can Google it. It's easy to find. Anyway, you can join, and there's multiple ways to join. You can join online. You can join via mail. The easiest thing is while you're here at a meeting, you just meet Brooks there at the back table, and what's that, white polo shirt back there, and he'll sign you up, and you can or renew a membership either way. So that's easy to do. There is a new member guide. Actually, if I back up, it's right there on that little blue button. You can see it on the page, new member guide. It's also a link at the bottom of every one of our web pages. It tells you what it is to be a member and that sort of stuff. So that's available to you as well. If you'd like to know what's going on here at the club, there's lots of different ways to find out. One of them, you can subscribe to our newsletter, or not our newsletter, our email distribution list. And the directions to do so are out there on our webpage. So you can just follow those directions. And I see usually, I don't know, sometimes 3-4 people a week signing up for it. So a lot of people are getting our distribution list. It's not a spam generation thing at all. So you don't have to worry about we're going to sell your email address to somebody else and you're going to get 1,000 emails from various businesses or anything like that. It's just for us. And we probably send, in the neighborhood of maybe 10 emails a month. It's not very much, usually meeting announcements, things like that. So that's one way you can find out what's going on here. Another way also on our website is to just go out to our events and meetings page and click on the calendar out there. And we have a Google Calendar on the page. And for instance, if you were to look at tomorrow night, there is a public event that we're sort of supporting out in Apache Junction. So you would see that event and you would see some of the details of that. And we are heading into the busy season. The skies, as we all know, are getting darker earlier now at night. It's no longer, sundown at 8:45. Sundown today was what, 6:22 or something like that. So we have a little bit longer evenings, and more importantly, we have cooler evenings. So we have a lot more star parties coming up at various locations. So this calendar will get a lot more full over the next several months as we have more and more events. We have a newsletter that comes out every month as well. It goes out to our email distribution list. It also is available on our webpage here. So you can always look at our newsletter to find out what's going on as well. And lastly, we have a Facebook page. So if you'd like to know a little bit more about what's going on, you can go to our Facebook page as well. And all sorts of things happen out there. People post photos of things they've been shooting with astrophotography. They'll post, hey, I'm going out to pick up post. Anybody want to join? We'll have a little star party out there. Lots of things. Actually, people sell used equipment and telescopes out there as well. So lots of stuff happens out there on that Facebook page. So if you would like to join, feel free to do so. There's about 1,000 people or so on that Facebook page right now. If you need equipment because you'd like to look at the sky, but you don't have any equipment to do so, we have a couple options for you. Also on our website out there. I notice there's a used equipment for sale. James, our property manager here, goes through all of it. So if we sell it, it's in pretty good working condition. So that's what I'm going to say, because he tries to refurb anything that's a little wonky or whatever. And anyway, the equipment's pretty good. And it's what, I don't know, is it a third of the normal retail price? Okay, so half to a third off the retail price, so or of the retail price, I should say. So yes, it's a good thing to do. We also have a number of pieces of equipment to rent. And the nice thing about renting is that you can try something before you go out and spend your bucks on it. So you wonder, well, do I like working a Dob? Or do I like working an SCT telescope? And so you can actually rent one for a week or two or whatever, try it out, see what you like. Or you'd like to say, wow, there's new little C-star telescopes. They look pretty cool. but I don't know. I'd like to have one and try it first. Well, we have one of those in the rental pool. So you can actually rent one of those little C-Star electronic telescopes that are, what, $500 these days, and you can try one out of the rental pool for that. So anyway, it's a nice way to kind of try different things before you actually spend your own money on it. If you would like to learn more, we do have a section on our website also that it walks you through various astronomy topics. Each one of those blue boxes you can click on, and it will take you to a section where you can read about whatever that topic is. And the last time I checked, there were 33 little blue boxes there. So 33 different topics you can explore on our website. So that's available to you as well. One of our charters, as always, is to give back to our community. So it's written into our sort of our group documents. And so we have the observatory right over here in the park. And so as you can see, there's lots of details there, but you can always sign up to be a volunteer telescope operator out there. If you don't know how to operate a telescope, we'll teach you. And all we need to do is have volunteers. And this is going to be the busy time out there at our observatory as well, because once again, the nights are getting longer and the nights are getting cooler. Last weekend, I worked over there, and I forget whether it was Friday or Saturday, but we had over 200 people come through the observatory. So it was a very, very busy night. So we had a fun time with everybody. Also, in addition to that, we have private star parties that we support. I mentioned we're going to be out in Apache Junction tomorrow night. A few of us with telescopes sort of supporting an event out there at Apache Junction. And this is the busy time of year, at least we're going into the busy time of year for this. So if you would like to help out, we would encourage you to do so. It's fun. You get to show the public your stuff. You get to see what other people's equipment looks like and how they're using it. So it's just a fun event to go out and spend some time at one of these star parties. And usually it's 2-3 hours out of an evening. And so it's not a huge time commitment, but it is very beneficial, very fun for everything. If you're happy to have this club, these are the people that sort of run the club. And I don't always put this slide up, but I put it up tonight for a very specific reason, because you'll notice that 4 of those names are in red. And so why are those 4 names in red? Those 4 names are in red because, special announcements, we have club elections coming up. So come September, that's the end of sort of our political year, if you want to call it that. And so we have elections that happen in the November meeting, because in January, then we have new officers for the club. And so we have term limits are taking out, actually, these 2 guys right here. So anyway, Woody is our vice president, and James is not only our property manager, but he's also our club secretary. So he takes all our notes and things like that. So both of these men have been doing this for the last 2 years. So they were elected, then they stayed on another year, and so now they're at term limits. So we need to replace these 2 guys. We also need to replace 2 board members as well for the same reason. They've just hit term limits. They have to move out. We need some new people involved. So anyway, we have just under 200 registered members in this club, and we need 4 of you, just 4 out of 200 to kind of maybe step up and offer to maybe serve in one of these positions. And I know that might make you a little bit nervous for a variety of reasons. So time commitments, probably 6 or so hours a month. You're sort of required to be in these meetings. So this is 2 hours of those 6. We have an online board meeting every month that usually runs an hour to an hour and a half over Zoom. So you don't even have to leave your house. So that's another little bit of a time commitment. And then there's going to be a few hours a month you spend doing your actual club duties or responsibilities or whatever that is. I figure roughly 6 hours or so. I think that's a fair estimate. Anyway, and if you're also nervous, not because of the time commitment, because you don't know how to do this, please don't be, because any of the former officers will help you out. And trust me, they're great help. I think I was a member here a year and a half when they asked me to do this and become president. And well, number 1, I'd never joined a club before. Number 2, I was very new to astronomy. And number 3, I've certainly never been a club president before. So I was a little shaky in my boots, but the former folks here, Woody, James, Claude, our former president, have been very, very helpful. And so I've survived. I've got through it. Yeah, there's been a couple of moments of anxiety here and there, but overall it works out pretty well. So, and in fact, these people aren't just going to help you for the first week or first month. Just 2 days ago, I contacted Claude, the former president, and said, I need some help because you did this last year and I've never done it yet. How do I do this? And so he was walking me through some things just 2 days ago, and I've been in the job 9 months now. So he's still helping me occasionally when I need help. So please volunteer. We need 4 people to kind of step up and maybe volunteer for one of these positions. And lastly, you can see if you want to talk to me in the meeting, that's fine. You can see the email address to let me know as well if you're interested. I'm not bashful about asking people. So I have some people in mind if I don't get volunteers, but definitely we might ask somebody. So anyway, in fact, ask our last 2 or our 2 newest board members if I'm bashful about asking, because our 2 newest board members are board members because I asked them. So anyway, that's enough of that. By the way, the election, if I think I said it on that slide, is in November. So we'll be electing whoever it is. Star parties, something a little more fun now. We have 26 people. It's full. So we have 26 people signed up for the Hyman Rim Ranch Star Party that happens next weekend. So all we're going to say is have fun. We hope you have clear skies. I can't go. I have a 50th high school reunion out in California that same weekend, but I wish I could join you guys. That would be a lot of fun. James here is going to be leading that trip, and they've had a few meetings to, I think, get things squared away. So you should guys have a lot of fun. The other thing we've got coming up in about, I think it's 7 weeks from tonight. I didn't actually look at a calendar. I could be off a week or so, but roughly 7 weeks, I think, from tonight, we are actually having our biggest star party of the year, the All AZ Star Party. So all of these details are out on our website. In fact, there's more details about the party out on our website, but I put the kind of the biggest things there, the most important things there. So we hope you join us for that. As you can see, it's a 2-night event. So it's a Friday, Saturday, November 1st and 2nd. And I'll be arriving on site probably about 1 o'clock on Friday. And but the porta potties and the hand wash station will be out there by Thursday afternoon. So if you go out the night before, you want to be there a night early, you can be. And there will, like I said, be porta potties and a wash station, things out there. Anybody can attend. We do have $5 for a dinner out there on one night. We have coffee and tea and snacks every night at 10. So it's kind of a fun event. I've done a few of these now. We are starting to get some nice raffle prizes for this event as well. We've been working for about a month with different folks out there in the community to get raffle prizes. And so we've got some really good stuff on the agenda. And so bring your folding money. And you can buy some tickets and hopefully you'll win some stuff. We've got some star trackers and we've got a telescope and we've got a few other odds and ends. It's really nice items actually. So we're looking forward to this. So anyway, just be aware of that. I will be asking for attendance numbers probably in the next meeting because that's just a couple of weeks before we go and I need to buy food. And I need to know whether I need to buy food for 50 or 100 or whatever it might be. So I need to know that. Speaking of things we did, we actually did support an event last Sunday out at Diamondback Stadium, and just a couple pictures there. So there's Don working with a couple of kids out at Diamondback Stadium. We took the meteor case, and based on the way he's holding his hands and the smile on his face, I think he just did his disappearing meteor magic trick. So he takes a little meteor for the kids and he makes it disappear. So anyway, it looks like that's what he's doing. There's Claude and Dawn at sort of one of the booths there. And actually, I was there as well. I was off to the side, and I actually took a couple of telescopes, and the telescopes were live. So I had the SCT pointed across the stadium where they could watch a TV back underneath inside the stadium on the other side. Everybody's like, wow, you know, they're all used to those telescopes you buy like at the toy store where you can barely see anything. So the fact that they could see a television on the other side just blew their minds. I also took a Sea Star with me, although it's behind me on a little table. You can't see it. And I had a Sea Star and an iPad there sort of also focused on that. And I think I probably sold some Sea Stars that day because everybody's like, how much is that? And I said, well, it's $500. where can I get one of those? So anyway, I probably sold a few sea stars that day. But anyway, it's a fun event. And there are perks of volunteering because I am now a proud owner of a Los Serpientes jersey as a result of that thing. So anyway, they gave us jerseys for being out there and supporting the event. So it's kind of fun. All right. One important announcement, usually for club members or Greco volunteers, people that have helped the club or whatever, we usually have a Christmas dinner every year in December. We have it in this room. We put a bunch of round tables here. We decorate it up. We have food, all that stuff. Based on the schedule of the Christmas lights in the park this year, we cannot do the Christmas dinner here this December for members or Greco volunteers. So we're not sure exactly what we're going to do yet. We have some ideas. We're planning on some fun ideas, actually. I'm hoping they'll work out. But we'll do something for members or the Greco volunteers in the first or second week of January is what we're looking to do. And we have a couple of things. I've been on the phone with some people, and we might have some fun. I'm hoping we can do something besides just a dinner. And so anyway, stay tuned for that. I'll have more details probably by next month at our meeting. A poll question though, if this event were to have food involved, we always bring Italian, and we always bring Italian for one reason, and that is it's the cheapest food. So anyway, but we have a little bit more budget now, so let's not always have to go with Italian. So this will just be a raise of hands. I'm just kind of curious, since we might have to buy food. You can raise your hand more than once, but how many are okay with Italian? Please raise your hands. So roughly half to 2/3 maybe. What about Mexican food? How many would prefer a Mexican food? So a little less. Okay, that's good to know. What about Asian food? So Asians kind of rights up there with Mexican. Okay, what about barbecue? Oh, okay, barbecue and Italian seem to be the winners. Okay, thank you. Very informal poll, very scientific, of course, but informal nonetheless. So anyway, okay, that's a good thing for me to know. All right, and now for the raffle. So everybody's got their tickets. I tell you what, James, why don't you pull the tickets out from there, and we'll do a double blind here. So, yeah. Yeah, go ahead, use the mic.
The winning number is 082143.
All right, back there. All right, we got one. Okay. Did you get the second one?
Oh, I only got.
Oh, you walked away? Okay. By the way, we're going to do this actually next month and November as well. So we keep wearing those badges.
Next number 082135.
All right, there we go.
You said there's another one?
Yeah. There you go, sir. You're all set. All right. All right. So that was fun. It's awful having to give money away. It's just so depressing. So anyway. Last week I managed to make sure that Bob Buchheim won, and the deal was he took me out to dinner, so it worked out great. So anyway, all right. Member presentations, announcements are done. We have member presentations, and speaking of Bob Buchheim, Bob's the first one up tonight. So Bob, you want to come up, and you can see the title of his talk here, and we'll let Bob take it away.
Thank you. Down arrow does it. All right. Thank you. For the last 12 years, I've been one of the instructors at the Mount Wilson Observatory Summer School for college undergrads, the Summer Observational Astrophysics Retreat. So I'm here to do two things, tell you a little bit about what I did on my summer vacation and interleave that with the legacy of George Ellery Hale. Hale was an insightful scientist, a remarkable program manager, and a man whose vision really transformed 19th century astronomy into modern astrophysics. three elements of that vision came together at Mount Wilson. The first idea was, if we're going to understand the stars, we must understand the sun. Second, if we're going to understand the universe, we must see it fainter and deeper and in more detail, higher resolution. And third, astronomical observations must be anchored in physics. The first one led to the science of solar physics. The second one led to a whole new set of instruments. And the third led to a physics laboratory in Pasadena, which gradually morphed into Caltech and Jet Propulsion Lab. Hale recognized the value of putting observatories on mountaintops with good seeing. Here he is on one of his first scouting expeditions on the top of Mount Wilson. An instrument was set up to measure the conditions, and finally he was able to send a report to the Carnegie Institution saying, this is the place, because they were going to fund much of the early work in the development of the Mount Wilson Observatory. Hale was first and foremost a solar researcher and a very skilled spectroscopist. He was the inventor of the spectroheliograph. So the first thing that happened at Mount Wilson was the construction of a high-resolution solar spectroscope. Under construction here, note the tower that the optics will be put on. Here it is, almost ready for the optics, the coelostat arrangement that collects the sunlight and sends it into the building, pointing it toward the primary mirror. That's, I think, a 24-inch parabola. The light from the primary mirror then is sent to a fold mirror and then directed down to the focal plane, where it makes an image of the sun on the slit of the spectrograph. The student here, you'll notice, is wearing welder's goggles, because that image of the sun is blindingly and painfully bright. With this instrument, the students at the summer school measure the differential rotation of the sun. It doesn't rotate as a solid body, and the 5-minute solar oscillations, the waves on the surface of the sun, which is the beginning of helioseismology. After that instrument, called the snow spectrograph, was put together, Hale discovered that the limitation to the fineness of the images of the sun was really driven by atmospheric turbulence from the ground up, ground turbulence. That's why he built that big pillar out there to put the coelostat on top of. But it became clear that higher would have been a lot better. And that resulted in the building of the 60-foot solar tower, which was great, but not quite what he was looking for. And ultimately, the 150-foot solar tower, the coelostat is up in the top there, and then the sunlight, now collected way up there in the air, is directed down a protected light path to the slit of the spectrograph in the control room, and then down a well to where the grating is underground, where conditions are absolutely stable, day, night, summer, winter, doesn't matter. And with that instrument, oh, and here's our students this year in front of the entry to the observing room of the 150-foot tower. With that instrument, Hale was able to focus the sun. You can see, oops, the sunspot. How'd that happen? You can see the sunspot. That vertical line is the slit of the spectrograph. So the light that you see hitting that vertical line is what goes through to the grating to be dispersed into a spectrum. And it was with this instrument that Hale first demonstrated Zeeman splitting. We had a talk that mentioned Zeeman splitting a couple of months ago. Who gave that? Magnetic field splits the spectral lines there in the sunspot. First time that it was demonstrated that sunspots are magnetic phenomena, and the amount of splitting allows astronomers to determine the magnetic field strength in that sunspot. As often happens, once a phenomenon is observed absolutely without question, lesser instruments are able to detect it. And indeed, a couple of years ago, our students demonstrated Zeeman splitting on sunspots using the venerable old SNO solar spectrograph that I showed you earlier. High fidelity observation at night of stars, planets, nebula, etc. Andrew Carnegie agreed to fund the development and construction of a whole new type of telescope at Mount Wilson, now known as the Mount Wilson 60-inch. First thing that had to happen was the trail up the mountain had to be widened and strengthened so that mule-drawn carts could take equipment up to the top of the mountain. A dome was created, and in the fullness of time, Hale and Andrew Carnegie were the proud parents of a new scientific instrument. Visual observing through the 60-inch telescope at Mount Wilson is different from what you're used to. You know how you'd be very careful to make sure you don't bump your telescope, you know, so that the image doesn't jiggle? This is visual observing through the 60-inch at Mount Wilson. In some orientations of the sky, the very best way to do it is to have one leg on the ladder and the other leg planted on the telescope as you lean over to the eyepiece. The telescope weighs 20 tons, so 100 extra pounds from you just doesn't matter. This instrument was used photographically to measure what we would call deep space, the solar system, photometry and spectroscopy of stars, and a long-term project at Mount Wilson was measuring the spectra of stars to search for things that were analogous to the 11-year sunspot cycle, which they found. A surprising, maybe not then, well, then it was, maybe not now, a surprising connection between the sun and the stars. Not too long after, a larger and more sophisticated instrument began, the 100-inch Hooker telescope. Pieces shown here. Here it is in all its glory as it exists today. I tell you, it is really hard to make a photograph that shows the scale of this monstrous machine. There are two guys on the observing deck just below the primary mirror. And when you stand there and that primary mirror and I don't know how many tons of mechanism is just kind of grazing your head and it starts to move, it is terrifying. It was designed as a photographic and spectroscopic instrument. This is the auto-guiding system. You know, a human being staring through an eyepiece, turning two knobs to move the plate up, down, left, right to keep the target object stationary on the plate through exposures lasting several hours, maybe longer, through nights where the temperature gets below freezing. And it was with this instrument that the discovery by Edwin Hubble of a Cepheid variable star in the Andromeda galaxy was made, thereby enabling him to make an estimate of the distance to that galaxy and starting the modern view of the universe, where those galaxies are duplicates of the Milky Way, countless numbers of them scattered through the universe. This year, one of our students had a project to make a spectrum of a nebula, and we had failed at that last year because we didn't have enough light. And so we tried an experiment, putting a modern commercial spectrograph on the 100-inch telescope. There's from right to left, Tom Meneghini, who's the Director of Telescope Operations, Paula Turner, who's the Director of SOAR, and our student Parissa, taking a spectrum through the 100-inch telescope, probably the first spectrum that's been made on that instrument in decades. It was beautiful. Most of the students' nighttime projects happen on this 16-inch Meade in that dome, and they range across the universe. Asteroid light curves, light curve and shape modeling of eclipsing binary systems, variable star photometry and spectroscopy, instrument characterization and atmospheric measurements, a whole array of projects that the students selected for themselves that we vetted and could be done during the 2 weeks available to them. Earlier, I mentioned high resolution. In, I think it was 1920 or thereabouts, Albert Michelson fitted this bar on top of the 100-inch telescope so that he could do 2 aperture interferometry and thereby hope to measure the size, angular size of individual stars. It worked. He was able to measure the angular size of Betelgeuse, the first time ever that a star's diameter had been measured, a stunning achievement of unprecedented resolution in astronomy. That tradition continues today at Mount Wilson with the Chara array, 6 1-meter aperture instruments scattered across the mountaintop. Their light combined into a single interferometer so that together they provide the angular resolution, the lambda over D, a diffraction limit of a mirror about 1,000 feet in diameter, not inches, feet. It is so accurate that you can see the mountain breathing as it gets hot, puffs up a little in the daytime, and then gets cool and shrinks a little at night in their data. We have had students do speckle interferometry projects using the 16-inch and measuring the separations of optical doubles at fractions of an arc second. And meanwhile, the folks at Chara are now making maps of the surface of other stars. Here's a surface map of Polaris. George Ellery Hale was born just a few years after the end of our Civil War, and he died a few years before the beginning of World War II in Europe. During his lifetime, he was responsible for building the largest telescope in the world 4 times. He made important scientific discoveries himself that transformed traditional astronomy into modern astrophysics. He also made the instruments and the institutions that allowed other people, Seth Nicholson, Albert Michelson, Walter Body, Edwin Hubble, to make their paradigm-shifting discoveries. He founded the Astrophysical Journal. And without him, Southern California may not have become a powerhouse of technology. If you'd like to learn more about Hale and his legacy, I recommend this movie, Journey to Palomar, and this book, The Perfect Machine, the story of the 200-inch telescope on Mount Palomar. If you know a college student who would like to participate in this 2-week Live at the Observatory event at Mount Wilson, point them to the Mount Wilson Observatory website where all the details are. So that's what I do on my summer vacation. If we have time for questions, I'm happy to entertain a few.
Questions for Bob? Comments? Corrections?
Bob,
Thank you.
Bob, quick question. Where did you get the image of the Polaris star?
Oh, it's from the Chara website.
Their website, it's on their,
CHARA, Center for High Angular Resolution
yeah.
Astronomy.
I think my wife would kill me if I printed one out.
Just curious, Chara, you said it had the equivalent of 1,000 foot. That's the distance between those 6 points total? Yeah, for those online, the question is the Chara 1,000-foot diameter mirror, is that related to the positions of the telescopes? And the answer is yes. If you kind of draw a circle around them, it's about 1,000 feet diameter. And there are at least 2 more instruments coming online. Just this year, they were getting them in place. There will be 2 mobile instruments, so they're no longer constrained to the 6 specific locations. One is probably going to be closer to the optical beam combiner building, and then one can be moved to 3 or 4 different positions around the observatory for both separation and angular position. And you know, I showed the picture of observing through the 60-inch. You can rent the 60 and the 100-inch for either a half of night or a full night. It's, as I think, a couple of $1,000s. So you get 10 or 15 people together and you can spend a night. It comes with a telescope operator, and it's a wonderful experience.
Any other questions for Bob? Yeah, just hold on a second. The people online on Zoom can't hear if we don't use the microphone. Thanks.
I'm just curious about the interferometry array because you use one terminology there as far as light pipes to central facility. So is that optically reflective conduit, meaning it's just pure optics conducting that light, or is it through like a light pipe, large light pipe like fiber optics?
Yeah, it's a light pipe. It's not fiber optics. The instruments, the 1 meter instruments, are afocal. So each of them puts out an optical beam about, I don't remember, 4 or 5 inches in diameter. That is then, there's a series of mirrors that put it on that picture. You can see these, you know, these lines here. Those are light pipes. They're I don't know, 8 inches in diameter, evacuated to a pretty high vacuum. So the light is literally sent to the beam combining laboratory, which is check out the Chara website to see that beam combiner. But you're making fringe patterns, just like you do with a 2-slit experiment in the physics lab, only here it's 6 being combined. Optical path length from each telescope into the beam combining lab has to be made accurate and identical to fractions of a wavelength. And of course, that changes as the star rises and sets, the distance to this one to that one. But it's a gigantic, amazing interferometer. Translates it into images of stars and systems of extraordinary resolution.
I sort of have to apologize to some of you because I've been a member of this group for about 3 years, and I really don't know a lot of you. And it's my fault because I've just had some busy years here. And so I haven't been making it to all the meetings, but finally here I am. So question you might have is, who is this guy with enough audacity to simulate the universe? I come from a career of engineering mathematics, and when I retired, I didn't want to lose track of some of my expertise, so I have been looking for something to simulate. And so I was telling everybody, well, I'm going to do everything. I'm going to simulate the universe. So that's how this came to be, but here we go. What does it mean to simulate the universe? Well, this, yes, is that area big enough? Should I try to make it bigger? Well, now I'm not sure I'll be able to run it though. Here, let's do this. Okay, let's see how that works. I'm going to do this a little bit backwards because I'm going to hit you with one of my best simulations right away, because otherwise we're going to run way out of time. So. Oh, okay, here we go. Okay, you may ask, well, what is this? Well, it's a piece of the universe. See, I'm simulating the universe, but I didn't mention that I'm doing that a little piece at a time. And the big white space here is outer space. And what we have to do to build a model is to populate it with things. So here are some things. And the center object is the sun. And the other colored objects are the inner four planets, the green one being Earth, and the blue is Venus, and the red one is Mars, and this one's Mercury. And if you will notice this tiny little silver sphere, that is a spaceship. In fact, what it is a shuttle that will shuttle back and forth between the Earth and Mars. And to get it going, we sort of tell it, to get going. Okay, if you notice, the Earth carrying the shuttle is approaching Mars, and when it gets to a appropriate spot, it launches the shuttle, which then locks onto Mars, and it continues until Mars is again within a shot of the Earth, which takes about 2 years. So in 2 years' time, we're going to be able to make another trip, this time going from Mars to the Earth. And then again, when Mars gets close enough, we're going to go from the Earth to Mars, and so on. It will go on forever until we quit this process. So these numbers that you see up in the corner here are the time increments going by. And for each one of those numbers, I create a new frame. And the thing driving this whole thing is Newton's laws. So all I did was create some objects and put in Newton's laws and told the program to, okay, compute what's going to happen. And it's computing what's happening with those objects in it. It's really kind of cool that the actual path traveled in the transit is, well, wait till the thing stops and I'll point it out. I'm doing too many iterations, I guess. There we go. Okay, so if you look at, say, a black line going from the shuttle to an intersection with Mars's orbit, that's the time actually spent in space. And then, what we're doing is the shuttle is falling from this orbit to this orbit. So it's actually only traveling this much, which happens to be about 40 million miles. So it's pretty big, but it's certainly better than having to go all the way across somewhere. And using this process, you're actually falling back and forth between the Earth and Mars and the Mars to Earth. The only time any power is being used is when you're launching. So this is an example of the mini universe. Now, how does all this come about? And we're gonna now go back to the beginning of my presentation. Problem is, I forget where things are, and I have to find them. I had to hit that clear button to get rid of all the stuff in memory. Okay, now if we want to create an object that's fairly simple, we say add a part and add another part and add another part. These are pieces of the universe. If I click on one of these parts that I just added, it opens a dialog which shows the properties of that part. So what I am showing here are the X and Y coordinates, the X and Y velocity of the object, and various other things, important stuff like the mass of the object and so on. Now, these objects could be planets, they could be stars, they could be atoms, they could be whatever you want. This is, after all, the universe we're working in. So you could be modeling atoms and using quantum mechanics to do the computations, which I'm obviously not, and will probably never get around to that. But the idea is to make it totally general. So it is totally general. Now, if I change some of these parameters, they will automatically take effect. But I can do it interactively. So for instance, if I want to set a vector that would be that would represent the motion of one of these objects, I click on the object and I set a vector saying that's going to be the initial velocity of that object. And then when I start it up, Newton's laws are going to take over and make this collection do what it's supposed to. So I hit on that, and the objects hit other objects. And again, using Newton's genius, we move things around. Okay, so the thing that is missing at this point is gravity. And actually, I had a slide where I was going to put some equations, but I'll forego that. I will assume you all know Newton's laws, but maybe a big assumption. But if you don't worry about it. This simulation is still fun. So what we want to do is well, I should mention that once I create a set of objects, then that becomes a model. And I can just save that model and then bring it back up and run it. So I have a set of saved models, and that space shuttle was one of the models. And what I want to do is show some others that that give you some notion of how the simulations are being done. Okay, I should mention that there are really two types of objects. Those which I call elastic, that when they collide, they bounce off each other. And there are inelastic ones that stick together. And some of these, well, I'll show you something called a butterfly. And after a while, I'll try to explain, if we have time, I'll explain why those are called butterflies. But in this case, we have a set of objects here. And one of the properties I have, if I click on the object, I can freeze it if I want to. See, that object is frozen. And all of these objects are frozen, actually, except for this one. So what I'm going to do is just run it. But this time, I got to point something out in settings. This time, I have gravity turned on. And I'll just ignore explaining how I did that for a moment. And I'll just let this thing run. So when we have gravity, that thing is moving because it has an initial velocity, and the gravity was pulling it toward the center of gravity of this stuff. And since the other ones are frozen, they won't move. But gravity is actually what's making what's making this move at this point. Now we have to go back to Newton again if we're going to talk about gravity. And let me show you we're at 15 minutes. That's why I started with the best model. But I tried this morning with Woody's help to do a test of how fast this was going to go. And he says, well, this is great. It's beautiful, but try to shrink it down to 15 minutes. And I found that impossible. And therefore I went in this roundabout manner. And actually, at this point, since we are out of time, I'm going to quit. And what I will say is that if you want to see the rest of this, we'll have to show you some other pieces at some other meetings, or set up something else if I don't know what we do, but I'm available to continue with this, but I will go faster the next time because at the moment I'm a little nervous, I think. So I will quit.
Did you write all of the software for that, or are you using some other system?
I wrote it all myself, and it's written in C#.
Okay, great, thank you.
And that was one of my, in the beginning, I was trying to figure out what language I should use, and I concluded C# was a very good one in that it had most of the scientific stuff that I wanted, and it had some nice ways like dialogues where you can easily communicate your data to it, and so I like that language.
All right, thank you, Ted. So our featured speaker this evening is Dr. Alan Strauss. He comes to us from Tucson, as I mentioned. He's the head of education and outreach for the Vera C. Rubin Observatory and a longtime amateur astronomer. And that was going to be my full introduction, except I asked him for a few things if he wanted me to say something else, and it's too much, Mike. That is Mike's idea, by the way. So please welcome Dr. Alan Strauss.
Can you hear me okay? Or do I have to hold this? You can hear me? It's okay? Or it moves probably? Good. So yeah, thanks. It was fun. I'll try not to go all the way for 45 minutes because, well, it's late and I'm usually in bed at 9 o'clock. So no, I'm kidding. I really enjoyed the Mount Wilson stuff as a longtime amateur astronomer. I like to say I am an amateur astronomer by training. My background is in education. I got my PhD from the College of Education at the University of Arizona in Tucson. You showed the book, Building the Perfect Machine. And so funny thing is that I worked at the university for a long time. Before I came to Vera Rubin, I was the director of the Mount Lemmon Sky Center and ran a lot of the education and outreach programs for Stewart Observatory down there, and was not looking for work at all. I loved my job, and I started reading that book. And within days of finishing it, the opportunity, I had applied for this job at Vera Rubin because it was the opportunity of a lifetime, and I was offered an interview. And so I referred to that book many times in my interview because of the similarities of, then building a telescope, working on a project that we just didn't know if we could accomplish, to Vera Rubin, right? Building something that's never been done before. So it was a perfect segue is all I'm saying. So that's me, that's the observatory, and the new name, the branding is the NSF-DOE Vera Rubin Observatory, because it's a jointly funded project from 50% by the National Science Foundation, 50% Department of Energy, where construction is almost finished, and you can see the observatory there in Chile. And if you go, I'm sure the question will be asked later, yes, you can get a public tour most Saturdays. So it's just by advance reservation. Okay, so what are we going to talk about? I'll give you a little overview of the education and public outreach at Rubin Observatory, which is my job. Why are we building the observatory? And the answer is not, why not? What is the Vera Rubin Observatory? And then we'll talk a little bit about citizen science, because I know that some of you have questions about how you can be involved. So the education and public outreach program, this is the mission, is to provide online data-driven experiences that are accessible and approachable, adding real-world context and opportunities for people to engage with Rubin Observatory and explore the universe. That predates me. I will say I've been there a year. It's a lot of words. We're working on a new one. But it is online, right, and data-driven, because as you're going to learn, if you don't know, the observatory is as much a data project as it is an astronomical one. Too far? No. So the education and public outreach really is formed into 4 groups in the observatory, sort of the outreach and content. And so, this is my day-to-day job. It's is this stuff. It's focused on the science-interested general public. That's you and I. There's the website, social media, all the communication things you would expect. There's a big formal education program. So that is really focused on preparing what we're calling investigations for high school teachers, high school and undergraduate teachers. I don't know why that says students there. And so the teachers are our audience, if you will. And these investigations will take advantage of real data from the telescope once it's flowing. And we're doing a lot of in-person teacher professional development around astronomy. Citizen science we'll talk about. And then of course there's a whole technical group because all of this is online. We don't get to have the fun that you do at star parties, unfortunately. So, you know, we're serving 8 billion people electronically, basically. Okay, now why am I showing you this slide, right? So Rubin Observatory is the first of its kind in many ways, right? Not just technologically, but it's the first government-funded observatory that has education and public outreach built into the program. Right? This is as much a deliverable, if you will, as the science itself. It's the first time the US government has done this. Certainly there are private observatories around the country that have education and outreach as central to their mission, but first government-funded one. So this is just a little graphic that, sorry, okay. Just a little graphic that shows kind of the organization. You have the operations and the data management and performance and education and outreach. It is central to the mission. So that's a takeaway. Okay, enough about what I do. Let's talk about the observatory. So why are we building the observatory? And by the way, I got a little grief for using this picture because my boss is like, hey, don't use a picture with clouds in it. But I explained to him that as amateur astronomers, you all know what happens when you get a new telescope, right? It's no different. It's just bigger and we have bigger clouds. So why are we building Rubin? So Vera Rubin, very famous astronomer, and what she did is she proved mathematically that what we call dark matter had to be out there, right? That most of what we can see in the universe accounts for very little of what must be out there. And so dark matter is core to the observatory's mission. And before it was named the Vera Rubin Observatory, it was called the Dark Matter Telescope. That was the original name of the project. She was a very strong advocate for women in science. And so this is the mission of the observatory, to produce an unprecedented astronomical data set for studies of the deep and dynamic universe, to make the data widely accessible to a diverse community of scientists, and engage the public to explore the universe with us. Okay, so you're going to start to hear a lot about the Legacy Survey of Space and Time, which is LSST. That was the name of the telescope after Dark Matter Telescope and before Vera Rubin Observatory. And so when Congress, the House, passed a resolution to rename this to the Vera Rubin Observatory, one of our lead software developers, who was sort of attached to the acronym LSST. And by the way, that stood for Large Synoptic Survey Telescope. She came up with the idea of, hey, let's call it the Legacy Survey of Space and Time. And the NSF loved that. So that's the 10-year science mission of the observatory. And this is very different, right? Most of the time you have a telescope and researchers put in for time, it goes to a committee, and if they're lucky, they're allocated time on that telescope, and they hope it's clear on their night. That's not what we're doing. We are doing a 10-year survey that the data will be accessible to all US and Chilean scientists with what we call data rights. So it's this optical and near infrared survey of the sky in 6 bands. And I'm not going to get too much into this because I am not an astronomer. But these bands are filters U, G, R, I, Z, and Y, and it covers essentially from the ultraviolet to the near infrared. And it's going to survey the whole sky that can be seen from Chile for 10 years, relentlessly, night after night, right? Minute after minute. As long as there is no cloud in front of the sensor, we're going to be taking a picture. And over the 10 years, we'll average about 800 to 1,000 visits to every field. That's a lot of stuff, right? So we anticipate that when this is done, that the catalog, the Rubin Observatory data set, this unprecedented data set, will have about 6 million solar system objects. Okay, so how many do we have now? within 1 million. Any ideas? Yeah, about 1 million objects, right? So that number is going to be pushed out to about 6 million. We'll have about 17 billion stars in the data set. Any idea about how many stars now are cataloged? Anyone? To about 2 billion, okay? And it will be about 20 billion galaxies. And all of these with exquisite photometry, image quality, everything. So this is really going to advance astronomy to places we can't even imagine. Okay, so this is the takeaway, right? Why are we building it? The bar chart. The universe. Dark energy, 68%, give or take. Dark matter, 27%. Everything we know, 5%. Okay. And then things that are made clearer by putting them in a bar chart, 0%. So this was Vera Rubin's contribution, though, right? Is when she began to look at galaxies, is that she estimated that only about 10% of the matter, or so she estimated that the sort of ratio of stuff that we can see and know about to dark matter was about 1 to 10, right? So she was not far off. So I mentioned that, you know, dark matter is central to the observatory's mission. So I love this quote from her: "Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the mystery lies." So again, 40 billion objects are going to be cataloged by this survey. That's more objects than humans on Earth. And we hope that this begins to give us a better understanding of dark matter when we see all these objects and how they are interacting with each other. The other key mission here is what we call the transient universe. So we're going to be scanning the sky relentlessly for 10 years, right? We're going to have the greatest time lapse ever made. And we're going to see all the things that change in the sky night by night. Well, once we have a good template. And it's going to open new windows into the universe. And for scale, I probably say this later, once we have a good template, on a, say, a busy night, we're looking into the plane of the solar system or something, we will probably detect about 10 million changes in the sky. Right? The numbers are truly astronomical. Okay, why are we building it? Because the government said so. So, I'm kidding. Every 10 years, there is issued by the National Academy of Sciences what we call a decadal survey, a decadal report in astrophysics, and it lays out priorities for the next 10 years. And so in 2010, what was then the LSST, now the Vera Rubin Observatory, was ranked as the top priority for United States ground-based optical and infrared astronomy. So that's the other reason that we're building it. Okay, am I speaking too fast? All right, what is Vera Rubin Observatory? Or where is Vera Rubin? So Chile, south of the equator. And that little pin, I believe, is where the observatory is. And it is a kind of fun fact that the latitude of the observatory south is actually pretty close to our latitude north here. So it's not bad as a guy from Arizona when you go down there, like, and it's fall here, it's spring there, and you have the right clothes. So. A little closer, so you can see the red pin in the center there. This is a little view. I don't know if you can read it there, but there's so where that bay is, there's a town, La Serena, that's where our offices are, and it's kind of the base facility, if you will. It's where we shipped the mirror by boat before it went up to the telescope. And then these did not come out as well as I wanted. We're down there in the lower right corner, and the reason I put it there is in the upper left corner is Cerro Tololo Inter-American Observatory, if you've ever been down there. They're basically kind of a ridge apart from each other. Okay, so the obligatory mirror slide. So what makes the observatory special? So the field of view of the system, and I say system because that's not just the mirror, right? It's the mirrors, the camera, is 3.5 degrees by 3.5 degrees. And I do not know why it says 7 moons right there. I didn't make this slide. But actually, it's about 40-something moons in the field of view, size of the full moon. It's going to observe the entire sky about every 3.5 nights. Now, remember, there's 6 filters. So when we say that, actually, it's going to scan the sky 6 times every 3.5 nights because it'll go through all of those filters. It's an 8.4 meter mirror, which is about the same size, or it's the largest mirrors we have right now. So the giant Magellan telescope, which is being constructed, will have 7 of these mirrors. The Large Binocular Telescope in Safford, if anybody's been there, has 2 of those mirrors, but it's about 25 feet across. Let's see. I don't want to, oh, I guess this moves, right? Okay, can you hear me now? So this is, these mirrors are to scale. So here's the Rubin one right here. And you can see that this 8.4 meter size is the same that's used in the GMT. The Magellan telescopes in Chile are 6.5 meters. This is the Hubble mirror for comparison right there. This is James Webb. So just to give you an idea of mirror sizes. Okay, so this is the other takeaway. When you think about the legacy survey of space and time, tell your friends WFD, wide, fast, and deep. Right? So that is like the science mission, science case for the observatory. There's been wide projects before, right? Wide surveys, there's been fast surveys, there's been deep surveys, but none of them have been as wide, as fast, and as deep as this survey will be. This graphic you see is what we call the WFD footprint. It's the latest version of it. So there's a science committee, represents scientists from all over the United States who are working on the survey strategy and cadence, and this is their latest model. And so the yellow areas are what we call the wide, fast, deep. So those are going to average 800 to 1,000 visits. This purple is the Milky Way, basically, that you see here. This is the area where the large and small Magellanic Clouds are. And it's not on this one, but there are also some what we call deep drilling fields in certain areas of interest. So it's going to do this every few nights, and it's going to take an image about every 20 seconds for 10 years, around 1,000 images a night. And the result is going to be this 800 frame time lapse and 6 filters of about 40 billion objects, right? So when this survey is done, it's really like 40 billion time lapses, if you think about looking at a single source. Here's some shots of the observatory. This is a little schematic, and so you can see it's actually about 10 stories from the bottom. So there's a machine shop down here. You can read all the things. This is the 3rd level. If you ever go visit, it's one of the more fun ones to be on. This is the coding chamber. And they've got the mirror in there, although of course it's not in there now. What's fun is that this is a platform lift here. So this comes down, right? And when we move the mirror up, which is going to be happening probably within the next 4 weeks, the mirror will go in the telescope. So it goes on, the lift goes up, and then slides in. You can see the telescope stuff there. We'll get to the camera in a minute. That was a picture of the camera in California before it was shipped to Chile. Telescope. Okay, so getting sharp images. I feel like pointing at the thing. You can see the picture there, the telescope. At the bottom, we have the M1, M3 mirror. So why do we call it M1, M3? Well, one of the unique things about this is that the single glass blank here, where we would normally call the primary mirror in a telescope, that first surface that the light hits, is both the first and third surface. So there's a secondary mirror, M2 up top. But you can sort of see on this drawing that there's the outer portion of this mirror. That's really M1, primary surface. So the light comes in, camera and secondary up there, goes up to the secondary, then down to this third surface here, and then up to the instrument. So that center, the M3, is actually a very steep curve, but this is a new design. The focal ratio, if you're curious, I think is f1.23 on the system. So it's very fast optically. I won't read through all of this. You can see though it's a 3.5 meter secondary mirror. And that inner surface, M3, is 5 meters of the 8.4. You can see the secondary mirror there on the upper left. That's on the telescope now. And then in this center picture, of the upper truss, you can see this is what we call a commissioning camera. So it's on the telescope now, and it has the same detectors as the main survey camera will. It just has one of them, as opposed to 189 of them. So once we get that primary tertiary mirror on in the next month, we will start actually commissioning the system. So among certain folks, in our office, they will tell you, we'll have a working telescope in a month. We're not going out to the public with that. We're not telling the NSF that because, the minute we do that, they want to see the pretty pictures and we're not there yet. But all that to say, those are later in my slides, that pretty soon in the new year, we will be collecting scientific grade data, and shortly after that, sharing the first images with the world. So wide, okay, it's a 3.6 degree field of view, and this is really important for the time domain science of the observatory. I've mentioned a lot of this. It's challenging. It's the largest camera ever made, period, not just for astronomy. Largest digital camera ever, 189 CCDs, 3.2 gigapixels, right? It's 3.2 billion pixels. That's a lot. 2-second readout time. There's a picture of the camera in the clean room and with some people to scale. This is my favorite picture. So this is actually the front lens on the camera, the first correcting element, with a person behind it for scale. It's the largest optic ever produced. It's nuts, right? So you've got this huge camera. If you wanted to display it, say at the resolution of your 4K TV in your living room, it would take about 380 TVs to display one image from the camera. Yeah, and then I don't know who does all the math on these things, but if you wanted to view all of the images on an HD TV at 30 frames per second, it would take you 11 months at the end of the survey, continuously at 30 frames a second. So like we say, the greatest movie of all time. Okay, but how do I explain the size of this to my dad? Well, you would be able to see a golf ball from 14 kilometers away with the system. So there must not be many golfers in here. Okay, so it's got to be fast, right? We got this wide optical system, and so to do this approximately every 3 nights, the telescope has to be able to move very quickly and settle very fast. So that was also a huge engineering challenge. I tried to bring the video, but I was told no, it's proprietary. But they took a little star tracker camera, they strapped it to the top of the telescope, and they've done some testing where they pointed at a star, they moved off the star, they slew the telescope back, and I have never seen anything like this where it just lands on the crosshairs and there's not even an oscillation. It's just boom, it's right there. So one day I'll be able to share that stuff with you, but apparently it's all proprietary for some reason. So the rapid cadence is important for very short-lived events such as eclipses and ultra-compact binary systems, supernova explosion, constraining properties of fast transients like asteroids, and then detecting microlensing. And so this could help us reveal really faint objects, dark matter, or exoplanets. Okay, we're gonna see if this will, we're gonna skip that. Deep, so the survey is gonna be deep. So at the end of the survey in the R filter, which is the middle filter there, it's going to be about to magnitude 27.5, which is pretty faint, right? And the survey is going to be about 100 times deeper than the Sloan Digital Sky survey. So you can see an image on the left there. It's about 1/4 of the diameter of the full moon there. So pretty small area on the sky. And then you can see a simulated image of the LSST of the same field. And I should say it's not just some theoretical simulation, but it's based on data from the Hyper Suprime camera on the Subaru telescope, which has a similar depth. Okay, and here's some images. So the one on the left is, you can see the first Oxtel image. So the Oxtel is a 1.2 meter telescope on the hill right next to Rubin that is going to be used to do calibration for the telescope, sky measurements, things like that. It also has a camera with the same sensor. And so we can test the data pipeline, things like that. And so that one on the left was the very first image taken through the camera. But on the right, you can see that this is a 6x5 arc minute image. It's a coad, meaning we've stacked 30 images through 3 of the filters. So that just gives you a sense of how sensitive this thing is. So 30 overlapping visits. Remember, this survey is going to be 800 to 1,000 visits, and we'll coad all of that data. Yes. So the takeaway: trillions of measurements of billions of objects. It's just too much data. We're going to need everybody to help us with it. But it is an international collaboration. There's data facilities. SLAC is the Stanford Linear Accelerator Lab in California. They built the camera. That's where a lot of the Department of Energy funding goes. And then we have in-kind partners in France and the UK where they have data facilities. So the main data facility is in California, the US data facility, but in France and the UK, we will have additional processing and also backup copies, if you will. So if the earthquake hits, we're okay. And then there'll be thousands of astronomers and physicists and you and I playing with this data for decades to come. So it is big data, right? So it's a 3,200 megapixel image every 20 to 40 seconds, 20 terabytes of data every night. In about 11 nighs, that's more data than the Hubble Space Telescope sent back in something like 28 to 30 years, right? Times are changing. Be over 2 million images collected with the survey. And so that's more data than 3 years of continuous video streaming or 50 years of music streaming. So by the end of the survey, that's over 60 petabytes of raw image data, which I am told is more than everything that has ever been written in any language. And this is one data set. Yeah, okay, so how am I doing on time? So it's 4 main science goals. We'll breeze through some of this. And so these are them: dark matter and dark energy, Milky Way structure and formation, cataloging the solar system, and exploring the transient sky. So I always say, if you're a researcher and your question doesn't fit into one of those, well, sorry. But okay, so back to Vera Rubin, right? So the dark energy, dark matter. She had been a student of Fritz Zwicky, who had theorized dark matter. And as she was observing that the stars and galaxies out on the periphery were moving too fast, right, for what was expected. And so as she made her measurements, that she published that dark matter dominates over stars, likely by a ratio of about 10 to 1. So the LSST, oops, I mentioned this, is going to map out around 20 billion galaxies. Right? We're going to have a picture, right? We're not, I'm going to skip that analogy, of the universe that to a depth we've never had before. And, again, we're looking at the space between the stars, right? We're trying to see the big picture here. We're going to be looking at gravitational lensing. So when there is a source, some light that gets its position or shape apparently changed by passing through what we call a gravitational lens. We expect to find a lot of that. Weak lensing, so this is the thing I'm having trouble wrapping my head around. This is not a great graphic, but I don't know who made this. On the upper left, it's just showing you an example. And so for example, this center galaxy, if you can see it up top, is actually round, but as it passes through this weak ripple in the gravitational well here, it stretches out the image that we see, or it changes the orientation. This galaxy is rotated from what you see on top. This one is inclined. So these are very hard things to detect without a very, excuse me, deep survey. Okay, supernova. So right now we detect something like a couple thousand supernova in 7 to 10 days, and we expect that we're going to be discovering those at a cadence nightly. Within about a year, it's expected there'll be more candidate supernovas discovered than in all of history to this point. And so these supernova, we call them standard candles often because they look very similar, are how we measure distances in the universe. Just big data, just keep thinking big data. This is another one of these mind-blowing things to me, time delay in these supernovae. So imagine we have a background galaxy that a supernova goes off in. And in the foreground, we have, a clump of mass that's lensing this, and we see supernova appear. And at some point later, at another visit, now we see it here. And then at another visit, we see it here. And we actually witness the time delay in that light getting lensed coming towards us. I don't know if I explained that well, but it's expected that we'll discover a few hundred, if not thousand, of these objects. Okay, so census of the solar system, I already mentioned, we have about, 1 million known objects. That number is gonna go crazy. People often ask about Planet 9. So you saw the simulation before the break of things, and these orbits are complex. The dynamics, when you have a lot of objects, get a little crazy, and there are certainly models and theories that do predict a Planet 9. And so everybody wants to know, is Rubin going to find Planet 9? And the answer is yes or no, but it'll answer the question most likely. So if it's out there, we'll find it. But if we don't find it, it's very likely it's not out there. So that's my answer. Well, we'll answer the question. Okay, so this is another big deal, is potentially hazardous asteroids. So we're going to detect a lot of faint things, a lot of fast moving things, and we're going to really need the public to help go through all this data. I'm conscious of the time here. So mapping of the Milky Way, right? When all of a sudden we're going to go from 2 billion stars to 17 billion stars, that's going to give us a much more detailed map and understanding of the evolution of our solar system. We're expecting to see, more detail, a better understanding of tidal tails around the Milky Way. And as astronomers simulate the evolution and perhaps future of our galaxy, they're going to have a lot more data to align their theory with. Back to Vera. So yes, there is no problem in science that can be solved by a man that cannot be solved, and my wife said to say better, by a woman. So she's usually right. Okay, so citizen science, it's too much data even for astronomers, right? So we have what's called the Rubin Science Platform. You can see the portal on the upper left, and that is what astronomers will go into to play with the data. It's a huge database, a lot of sophisticated tools. And remember, at the end of this survey, there's 40 billion objects in the Rubin catalog. There'll be about 1,000 measurements, each with a few dozen measured parameters for each of those objects. So it's going to be, in some ways, an impossible task, right, for an astronomer to go through all of the data that she may need for her project. So I'll skip that. So the education outreach team, one of our big projects is to work with Zooniverse. Anybody heard of Zooniverse? Okay, good. So they're an in-kind contributor. I'll show you their webpage in a minute. And we're building tools on the Rubin Science Platform that will allow the researchers to essentially easily and quickly create projects on Zooniverse. So, if they have literally 25,000 candidate supernova, they can get those image cutouts into a pipeline and onto Zooniverse very, very quickly. There's Zooniverse. So many of you are probably familiar with their early project, Galaxy Zoo. Right now they're in all the natural sciences. And do people want to participate? They do. I grabbed this graphic this morning at about 9 a.m. 835 million classifications have been done on Zooniverse by almost 3 million volunteers. So this is the real computing power of Rubin, right? Is you guys and the other 8 billion people out there. Okay, now some of you have observatories, right? All right, and you're interested in this stuff. So how can you contribute? Well, first of all, you'll want to get on Zooniverse when you can't sleep at night or when your telescope is collecting data, on the Andromeda galaxy or something for a pretty picture. But if you want to actually do, say, follow-ups, right? Do some photometry of an asteroid or something like that, You're going to want to sign up for one of what's called an alert broker. And so what these are platforms. There's 8 or 9 of them right now around the world that will serve up Rubin data. So all of these alerts are transient things, right? Candidate supernovas, asteroids, variable stars, moving objects. And so you create an account, you set up filters for the things you're interested in, and you hope that the machine learning going through 10 million alerts sends you the right ones. I'm kidding, it'll work, guaranteed. But this is the main way that the data will be served up to the public, is through these alert brokers. The bigger products, right? The co-added images that we have data releases every year, those will really be on the science platform for astronomers. But the things that you might want to do with an observatory, you would get through these alert brokers. And so this one you can see the screenshot of, is called Lasser. I think they're in Ireland, and I haven't used these, but the reason I put that one first is I was told they have the best tutorial, and it's really easy to create an account and then set up your filters in there. Here's a couple more. Allersay, I think is how you say it, automatic learning for the rapid classification of events. That's a Chilean one, one of our partners. The one on the bottom right is actually from where I work at the National Lab. But there's a lot of these out there. If you start doing an internet search on alert brokers, you'll find them. Okay, so I mentioned, when does all this start? Yesterday. So I stole this from one of the project things. I don't know, I'm supposed to share it, but there's nothing secret here. So you can see on the far left was December of 2023, and it comes up to August of 2025 here. And so the red stuff is basically glass, if you will. And so you can see we are in October of 2024 almost here. You see the red diamond there, M1, M3 cell on the telescope mount assembly. That's going to happen any day. Back here, the green was the secondary. That's already on. The blue is the camera stuff. So you can see that the commissioning camera should be on Sky pretty soon as we get that mirror on there. This is the survey camera. It's already boom, boom, boom in Chile. This has happened. It's where are we? Yes, this is where we are now. We're in re-verification. So I saw this morning the camera was at minus 100 degrees Celsius and humming along nicely. The camera is slated to go on. Yeah, this is current around New Year's. So we'll pull off the commissioning camera, put on the real camera, and keep going. And then you can see all the engineering. ORR is operational readiness review. So that's just the NSF and the DOE saying, okay, you can actually start the survey. What I do not see on here, oh, okay, so yeah, so you can see first light we're hoping is in May. And that first light, that's a public event, right? That's when we share pretty pictures with the public. It's not the actual first light of the telescope. So that's what we call first photon. And that'll probably be out of focus and nothing that you really want to see. Yeah. So also a word of like managing expectations. So we all love to see, you know, the latest and greatest picture from James Webb, right? They're amazing, they're beautiful, they're in color. That's not what our images are going to look like, right? This is a very wide field instrument. So that's what you're going to be looking for. Think of things like galaxy clusters and moving objects. And so we're starting to think about how to prepare the public for that, because, you know, you guys are an understanding audience, but, you know, we need the New York Times reporter to go, oh, that's really cool. when it's not going to look like James Webb, right? It's not a high resolution picture of the Horsehead Nebula or something like that. These are very wide field images, or, you know, hopefully we'll put out, I'm not on the committee, but I'm hoping we put out a movie of some transients or something, right? That people can see, oh my gosh, there's 100 supernova that brighten up in this image online. So what else? Okay, I will try to show this movie because why not? I think it's going to take us online though. See what it does. Yep. Okay, that didn't work. Never mind. It's not showing that on the screen. Oops. Okay, well, don't ask me how to get back to. Oh yeah, there we go. Never mind. It was a video linked to YouTube, but it's not coming up. It was just the dome rotating. Unless I can, oh, maybe I can figure it out. Ah, technology. Okay, well, I hope that was worth I didn't speak too fast, and well, we're really in trouble now. Crash the system. Well, the next slide just said thank you, so. I don't know why this is. Oh, all right. Now it says thank you. So. And social media.
Alan, I've got two questions for you. You mentioned a magnitude in R band of 27.5 approximately. How bright an object would saturate the sensors?
Did Mike put you up to this? Oh. So, yeah. So let me say two things. One, I am not an astrophotographer. So, you know, the minute we start talking about cameras and pixels and things, you know, my eyes usually roll back in my head. But I am told that the sensor saturates around 17th magnitude.
Okay, so that's beyond the reach of most of our small observatories. The other question would be in terms of transients, and I guess that answers it for T Corona Borealis because it's only around magnitude 10. And if and when it goes, it'll maybe reach magnitude 2. So this will be blinded by an event like that if it happens to be looking there. Okay.
I mean, I don't know how they're dealing with that because obviously there are bright stars all over the sky, right? So, yeah.
Questions?
While he's moving the microphone, you know, I will tell you one question that comes up a lot too is about satellites, you know, in the sky, and I had a slide, I took that out, but right now with the auxiliary telescope and the commissioning they've been doing there and looking at the satellites, we're anticipating about 1% of the pixels will be lost to satellites, which is not a catastrophic amount. I mean, it's not nothing, but that's kind of what we're planning for right now. So.
I had two questions. I was recently reading about rate of.
Hold the mic.
Oh, I was recently reading about rate of expansion, and you mentioned you know, the standard light. Also, I wanted to see, is that anyway helpful to understand? Like, I think there are two different teams working on finding. I think it's called Hubble constant. So, is this data going to help that in any way?
So again, I'm not an astronomer. I don't even play one on TV. But I think, yes, I think that, you know, all of this is going to help astronomers answer some of those questions, right? And further push the exploration of competing theories. And yes, it could help constrain the, you know, expansion properties of the universe for sure.
Right.
And if that's what you're asking.
Yeah. And the second question, so the public outreach program, is that going to help identify the objects that are captured by it? And like, will that in future help create a machine learning model that can automatically identify?
Yeah. So what projects are put out there, I have no idea because we're counting on astronomers. We're building the infrastructure for the astronomers to put projects, say, on Zooniverse. But there is talk of projects, yes, that will be specifically towards improving the machine learning for these because I mean, we have to have some pretty rapid classification, right, in these alert brokers so that, you know, if somebody's interested in getting alerts on supernova, that they're getting the right alerts, things like that. Yeah, it's pretty wild.
Okay, Alan, most professional observatories, you know, you have real regimented, you get like 3 nights or 4 nights or half nights. Does this survey, is it just not have that? It just goes across the sky?
Yeah,
you don't
10
really
years.
have scheduling. It just.
Yeah, well, there's a scheduler because they'll be, you know, putting this survey cadence in, and then, but there are observers every night, and so they'll also be, if there's clouds in the west, they'll, you know, go to the east, things like that. There's, I think, 3% of the time is also, is a video playing. 3% of the time on the telescope is also reserved for like targets of opportunity. So there's a gravitational wave detection right, that they ask for follow-up on, we might move the telescope and see if we can get something like that.
Okay, we've got some online questions.
First one, sounds like a huge amount of data. How can that be stored, managed, and analyzed to produce information?
Yeah, so there's probably as much money in the project from the NSF and the DOE into the data management as there is anything else. It's probably half our staff. So there's a US data facility that was built just for this in California. And I will tell you, in terms of mind-blowing things, besides 3.2 gigapixels, when the shutter closes on the camera, right, that has about a 2-second readout time. Then it goes by fiber optic to Santiago, Chile. It goes to, I think, Sao Paulo, Brazil, comes under the ocean floor up towards, I think, Houston, and then heads over to the data facility at Stanford University. Right? Then the machines do their thing and the alerts go out, and right now it's taking about 58 seconds from shutter close to alert production. Yeah, now imagine that at a scale of millions per night. So it has driven supercomputing in ways also.
Next question was, please forward a message. This is a little technical. Message to software engineering design team. You've built C++ wrappers on top of Python AP layer. I think it needs to be done in C++ API first, and then Python API on top of that. Performance will be significantly better.
Noted.
That's all the online questions we have. Thank you.
Another cool thing, I mean, if you're into trivia, is that so the shutter on the camera, it's got 2 shutters because the sensor is so big that if the shutter opened, right, the side where it started opening would get more light than when it closed, right? Than this side. Does that make sense? So it's got a 2-shutter system essentially. So it'll open like this, right, and then it'll close, and then the second shutter will close like that. And then the next exposure, it'll open and then it'll close so that they get the same amount of light to each end of the sensor. Every time I go there, I learn these weird, amazing things like that. But.
Okay, I've got one other question for you. Okay, since part of your charter is tracking asteroids, do you yet know what the smallest type of asteroid you can be able to track with this? Because obviously large ones like Apophis is no problem, but the ones that are probably 100, 200 meters in diameter are, while not planet threatening, they are city threatening.
Yeah, so already we're not we, Rubin, we, the world of planetary defense, right? We're finding asteroids on the scale of like a meter in diameter, right? So it's more about how much light are they reflecting and how close are they to us. So 4 weeks ago, there was one discovered, Catalina Sky Survey on Mount Lemmon, just north of Tucson, that you probably saw online, came into the atmosphere over the Philippines and blew up. That was about 3 feet in diameter. So very small. Yeah, we're trying not to be boastful because we don't know what'll happen, but there's a pretty good contingent of the Rubin science, solar system science community that feels that the survey will complete NASA's mandate of cataloging 90% of the objects in the solar system. So now there are plenty of people who don't think that'll happen either.
Other questions?
So jumping ahead 10 years, is there a plan for a northern sky survey?
Northern sky, I don't think so. Right now, if I would say anything, it's call your congressman and encourage them that the United States Extremely Large Telescope Program needs both the Giant Magellan Telescope and the 30-meter telescope. So not to get political, but the 30-meter telescope would be a Northern Hemisphere instrument. And I don't know what camera they're putting on, but we're just starting to have conversations about would there be a follow-up survey, or would there be a new camera? Who knows how technology will change, but right now we're just trying to get to the operational readiness review, to be honest.
Okay, any other questions? That's it?
Go visit. It's fun.
Yeah.
believe me.
I know, so do I.
All right, everybody. First, couple things. First, I wanted to thank Ted for speaking tonight. I wanted to thank Bob for speaking with us tonight and giving us their time, and our main speaker, Dr. Alan Strauss.